So imagine you open your phone and, hit save on a video.
Right, something we all do like a dozen times a day without even thinking about it.
Exactly. And somewhere out there in the world, a physical hard drive actually spins up to record that data. And it seems instant.
Yeah, totally seamless.
But think about what happens when a billion people do that at the exact same second. I mean, if you just stack up normal hard drives and servers, the traditional data center literally catches fire.
Oh, absolutely. The infrastructure would just melt down under that kind of concurrent load.
Right. So today, we're looking at a blueprint that actually solves this. We are doing a deep dive into a highly technical architectural design document on a masterless, decentralized storage system. It's called Ceph.
And it is a genuinely fascinating piece of engineering.
It really is. And if you are wondering why you should care about the deep plumbing of data centers, well, it's because you and I, and everyone listening, are generating exabytes of data every single day.
Yeah, the sheer volume is hard to even wrap your head around.
Right. And the old ways of storing it are just hitting a massive brick wall. So understanding this document is essentially a shortcut to understanding how the future of massive scale infrastructure actually works.
It really gives you a glimpse into the next decade of cloud architecture.
Definitely. But to appreciate this radical solution, I feel like we first have to understand the failure of the old systems. Like, what exactly is this centralized metadata wall that classic massive storage systems, I think the source mentions Google File System or Colossus, ended up crashing into?
Well, to understand that wall, you really have to look at the fundamental flaw in how centralized file systems operate. Basically, they all rely on a single master controller.
Like a central brain.
Exactly. Think of it as the central brain of a server cluster.
Mm.
This master controller has to track the coordinates, the directory paths, and the file names of every single storage block across thousands of hard drives. It essentially keeps a massive index. And even if you try to split that massive database across several different master servers, which is a technique called horizontal sharding, you still have a problem.
Because they still have to ask for directions.
Right. Every client machine trying to read or write a file still has to talk to a master controller to get the map. They have to ask, hey, where does this data live? Or where am I actually allowed to write this?
Right, yeah.
And that creates massive cascading bottlenecks as the system scales up.
Okay, let's unpack this for a second. Let me see if I'm tracking the bottleneck here. So traditional storage is basically like a massive physical library with, I don't know, 1 billion books.
That's a good way to look at it.
But there is only one librarian sitting at the front desk holding the single master catalog.
Mm-hmm.
So every single time you want to check out a book or return one or even just find out what floor a book is on, you have to stand in line to talk to that one specific person.
That is a brilliant way to visualize it. And if we connect this to the bigger picture detailed in our sources, that librarian analogy perfectly illustrates the 3 fatal physical flaws of the centralized model.
Okay, what's the first flaw?
First, you hit what they call CPU queue saturation.
CPU queue saturation.
Right. When millions of concurrent read and write requests flood in, everybody needs to talk to the master controller at once. This causes severe lock contention.
So it's basically a traffic jam.
Exactly. In software terms, the master server CPU is so overwhelmed just managing the waiting line, it doesn't even have the processing power left to actually move any data.
Wow. So the line for the librarian literally wraps around the block, and the librarian spends all their time just, like, telling people to wait.
Exactly the problem. They're just managing the line, not checking out books.
It sounds miserable. What's the second flaw?
The second flaw is RAM limits.
Yeah.
So in these classic systems, the directory hierarchies, the master index of where everything is, they're stored in volatile RAM for speed because you want really fast lookups.
All right, RAM is much faster than a hard drive.
It is. But RAM is finite. It physically runs out. If your dataset grows to include billions of small individual files, the sheer size of the metadata index completely exhausts the physical RAM capacity of that master server.
Oh, I see.
Yeah, you literally run out of memory just trying to remember where your data is stored.
Which means our poor librarian's brain is completely full. They just cannot memorize any more book locations.
Right, and the whole system just halts. And then the third flaw, this one happens during an emergency, is network choke points.
Like if something breaks.
Yeah. Let's say a server rack physically loses power. The master controller has to coordinate a recovery. It has to scan its index, figure out what data was lost, decide where to put the new backup copies, and then command thousands of servers to start moving data.
That sounds like a lot of network traffic.
It is. This centralized coordination completely floods the network switches with replication traffic. Because everything routes through the master knows commands, the master becomes a literal choke point for the entire network. The system physically cannot respond fast enough to achieve the sub-10 millisecond real-time latency that modern applications demand.
All right, so if the master controller, our single librarian, is the bottleneck causing all these CPU traffic jams, running out of physical memory and choking the network during a crisis, I mean, how do you find anything if you just fire the librarian?
That is the million-dollar question.
Right. If there's no central index, how do we run a massive storage system without one?
Well, you have to completely change the paradigm. If you eliminate the central lookup index, the clients need an entirely new way to find their data.
Okay, so what do?
The genius of Ceph is moving the system from searching to calculating. Instead of asking a master database where data is stored, the individual clients use their own local CPUs to mathematically calculate exactly where the data lives.
Wait, I need to push back on that.
Sure.
Because if every single computer on the network is just doing independent math to figure out where to put a file, what stops two computers from accidentally doing the exact same math and try to overwrite the exact same hard drive at the exact same time?
Yeah.
It sounds like total chaos.
And it would be chaos, honestly, if the math was random. But Ceph offloads that work using something called the CRU-esh algorithm.
CRU-esh.
Yeah. It stands for Controlled Replication Under Scalable Hashing. It is a deterministic, pseudo-random mathematical hash function.
Okay, deterministic meaning like it always produces the same answer.
Precisely. It's a fixed mathematical formula. If you feed the exact same file name and the exact same cluster map into the CRU-esh algorithm on two completely different computers,
Right.
both computers will independently crunch the numbers and arrive at the exact same physical hard drive as the answer.
Oh, wow.
They never have to talk to each other to coordinate, and they never have to talk to a central master lookup server. The client just does the math locally, figures out the destination, and routes the data directly to the disk.
Okay, but for a client to do that math, it still needs some idea of what the storage cluster actually looks like, right?
Yes, absolutely.
Like, it needs to know how many hard drives actually exist in the data center before it runs the formula. Or it might try to send data to a hard drive that doesn't even exist.
That is the missing piece. And it is handled by what Ceph calls the Paxos monitors, or the MON group. But this is crucial. These monitors are not librarians.
They don't have the master catalog.
Exactly. They do not track file paths. They don't know where your photos or your databases are stored. They only track the high-level physical health of the cluster. Things like, did a hard drive physically die? Or did an engineer just plug in a new server rack?
The source actually mentions they use a Paxos consensus state machine for this. I've heard that term thrown around in distributed computing, but what does it actually mean in plain English?
Oh, for those who aren't distributed systems engineers, Paxos is essentially a strict voting system. You usually have just 3 or 5 of these monitor nodes. If a hard drive goes offline, a single monitor cannot just declare it dead on its own. The monitors must take a vote.
So it's democratic.
Yes. A strict majority must agree that the cluster map has changed before an update is published. And this prevents what we call split-brain chaos, where, half the network thinks a drive is alive and the other half thinks it's dead.
That makes total sense. So these monitors hold the vote, update the map of the physical hardware, and then send that map to the clients.
Right. And because they only track the broad physical layout of the cluster, not the billions of individual files, the map updates they send to the clients are tiny. We're talking just a few kilobytes of data.
Oh, that's nothing.
Exactly. The client caches this light-rate map, which they call the OSD map, runs the CRU-esh math locally on its own processor, and then bypasses the monitors entirely for all the heavy lifting of reading and writing data.
Okay, so doing the math to find a drive makes total sense if I'm saving like a tiny text file or a single photo. But what if I'm an enterprise database running a massive 100 gigabyte virtual disk image? A math equation can't just shove a 100 gigabyte file onto a single hard drive in the cluster without blowing it up. How does the system handle massive files?
So Ceph solves this by completely unifying its storage. It has 3 consumer-facing interfaces. There's RBD for virtual disks, CephFS for shared folders, and RGW for cloud APIs, which is similar to Amazon S3.
Right.
But the secret sauce is that all 3 of those interfaces sit on top of one flat underlying layer called the Rados object pool. Rados only speaks one language, flat, fixed-size objects.
So it forces everything into uniform blocks. The source document actually focuses heavily on the RBD, the Rados block device, as the rawest, highest performance layer.
It does, yes.
If I hand the RBD a 100 gigabyte virtual disk, what actually happens to it?
The client-side system library acts as a slicer. It intercepts your massive 100 gigabyte volume and violently chops it up into uniform 4 megabyte Rados objects.
Tiny chunks.
Exactly. The server cluster doesn't have to manage this massive file at all. The client just slices it into tens of thousands of perfectly sized 4 megabyte chunks, assigns each chunk a sequential object ID, and then runs the CRUSH math on each individual chunk to scatter them across thousands of drives.
Oh man, let me see if I can run the math myself based on the design document.
Go for it.
Let's say I update a tiny piece of data, just 4 kilobytes, sitting exactly at the 150 megabyte mark of my giant virtual disk. Instead of asking a master server where that goes, my client just divides my 150 megabyte location by the 4 megabyte chunk size.
Right.
And 150 divided by 4 is 37 with a remainder. So my client instantly knows, this specific update belongs inside object index number 37. It wraps it up, calculates the server for object 37, and blasts it over the network.
You've got it. It's brilliantly simple. The client has done the math, sliced the data, and sent it directly to the target storage node, which Ceph calls an OSD, or object storage daemon.
Here's where it gets really interesting to me, though. The client sends the data straight over the network to the physical machine, the OSD.
Right.
But operating systems like Linux have been handling the job of saving files to hard drives for decades. Once that chunk arrives at the server, wouldn't Ceph just let the Linux kernel do its normal job of saving the file to the disk?
You'd think that would be the obvious answer, right? Why reinvent the wheel?
Exactly.
But ironically, leaning on standard operating systems creates an entirely new disaster at this scale. What's fascinating here is, if Ceph relied on standard PSX file systems like xdic4 or XFS on Linux, it would run into a massive performance penalty known as the double journaling problem, along with severe context switching delays.
Wait, context switching. I need an ELI5 for that.
Sure, think of the Linux kernel virtual file system, or EFS, as a toll booth on a highway. It acts as a middleman between the software and the physical hard drive.
Okay, a toll booth.
Every single time a read-or-write command comes in, the processor has to switch from user space into kernel space. It's like having to stop your car, roll down the window, and pay a toll every single time you want to move a tiny piece of data.
Oh, that sounds awful.
It is. It wastes massive amounts of processing cycles, and the double journaling is even worse. Standard Linux file systems maintain their own internal write logs to prevent data loss.
Right, like a backup ledger.
Yeah. So if Ceph writes a piece of data, it gets logged by Ceph software and then passed to Linux, which logs it again on the hard drive. You are physically writing the exact same data to the spinning metal twice. It literally cuts your write throughput in half.
That sounds incredibly inefficient when you're dealing with exabytes of data. So how does Ceph actually bypass the Linux toll booth?
Well, they built a custom engine from scratch called BlueStore. BlueStore completely ignores the Linux kernel VFS.
This skips the toll booth.
Completely. It ignores the Linux page caches, and it ignores PO6 file locks. Instead, it uses direct memory access, specifically calling a flag known as odirect to stream raw byte sectors directly to unformatted naked hard drives.
That is wild. It doesn't even format the drive, just talks straight to the metal.
Direct to the raw block. But the engineering goes even further because BlueStore handles massive files and tiny files entirely differently.
How so?
For large writes, anything in the megabyte range, BlueStore streams the payload directly to the raw disk blocks. It completely bypasses its own internal write-ahead log to maximize bandwidth. It just blasts the data straight to the drive so you don't suffer any double writing overhead at all.
But what if I'm just updating a tiny database record, say a small write in the kilobyte range? If you try to write tiny fragments directly to a raw spinning hard drive, doesn't the physical mechanical arm of the drive spend all its time just like jumping around?
It does, and your performance tanks because of those physical seek times.
Right.
So for small writes, BlueStore pulls a really clever trick. It defers them. It packages that tiny payload and writes it instantly to a highly optimized database called RocksDB, which sits on a super fast solid-state drive.
Okay.
It logs the write there and immediately tells the client, yep, your data is safe. Then, later in the background, a worker thread gathers up thousands of those tiny random writes, sorts them logically, and flushes them down to the slower raw storage disks in one clean, continuous batch.
Oh, wow. So it converts slow, random tiny writes into blazing fast sequential writes.
Exactly. which massively boosts IOPS, the input-output operations per second.
Okay, so the clients are doing local math to completely bypass the central librarian. And the BlueStore engine is bypassing the Linux operating system to write to the raw metal blazing fast.
Right.
But this entire architecture relies on thousands of cheap commodity hard drives. And hard drives break constantly. If we strip away the master controller that monitors everything, how does the system even know when a drive catches fire or a network cable gets cut?
It uses something called the Gossip peer-to-peer OSD heartbeat mesh.
The gossip mesh. Let me guess an analogy for this. It's kind of like a neighborhood watch program where no one actually bothers to call the central police station.
Okay, I like where this is going.
Instead, the neighbors just constantly yell over the fences at each other to make sure everyone on the block is still alive.
That captures the essence of it perfectly. Every single OSD server runs continuous heartbeat checks with its adjacent peers. And there is a vital technical distinction here. They use UDP protocols instead of PCP.
Why UDP?
Well, TCP requires a formal digital handshake, which creates socket lock queues, basically polite waiting lines to establish a connection. UDP just shouts the packet into the void.
Ah, no waiting in line.
Exactly. It bypasses those heavy lock queues, meaning the heartbeat checks are instantaneous and never block the main processing threads.
So what happens if a neighbor doesn't yell back? The source document talks about something called a gray fail, which sounds super ominous.
A gray fail is, honestly, one of the hardest things to handle in distributed systems. It's when a node isn't completely dead, but it's suffering severe hardware congestion.
Like it's just stuck.
Yeah, maybe the mechanical head of the hard drive is stalling, causing a massive latency spike. It's sick, but not dead. Because the peers are constantly checking heartbeats, they catch this latency degrade instantly.
How fast?
If a node drops its heartbeat for exactly 20 seconds, the neighbor flags it as dead, gossips that failure downstream to all the other peers on the mesh, and notifies the MON cluster.
And then the monitors step in.
Right. The MON cluster then holds a vote, updates the map, and increments the global epoch version.
This epoch versioning leads to one of my absolute favorite mechanisms in the whole design document, zombie fencing.
It's such a cool concept.
Because my first thought was, well, what happens if that stalling hard drive suddenly wakes back up a minute later?
And if we connect this to the bigger picture of data integrity, a zombie node waking up is incredibly dangerous.
Because it doesn't know it was dead.
Exactly. Imagine OSD5 has a network freeze. The cluster assumes it's dead, updates the map to epoch 43, and automatically promotes a new primary server to take its place. But OSD5 wasn't actually dead, its network switch just glitched.
Right.
So a minute later, OSD5 wakes up as a zombie. It is completely unaware that the world has moved on. It looks at its local memory buffer and tries to finish processing an old client write from back in epoch 42.
So it's literally trying to overwrite current data with obsolete garbage.
Exactly the risk. It reaches out to its replica nodes to commit the old transaction, but the replica nodes audit every single request.
They check the timestamp, basically.
Yes, they see OSD5's packet is stamped with epoch 42, but the replicas know from the gossip mesh that the current cluster reality is epoch 43. They instantly realize OSD5 is an obsolete zombie and they reject the transaction.
That is so clean.
It is. The zombie is digitally fenced off, and data corruption is completely prevented without any human intervention.
Okay, so what does this all mean for the end user? We've seen how the system writes data, how it bypasses the operating system, and how it fences out zombified drives. Let's bring this all together.
Sure.
Walk us through what happens when I just double-click a file to open it. How does this masterless mesh retrieve my data, and what if the data itself got corrupted while sitting on the disk?
The read query pathway is incredibly lightweight. When you hit open, your client looks at the file size, slices the request, hashes the object ID, and runs the CRUSH math to find the primary OSD server.
Okay, so it does the math again.
Yep. It establishes a direct TCP connection to that primary server and simply says, send me this object. Because it's just a read request, the primary server doesn't have to worry about writing to logs or coordinating with replicas.
It just grabs it.
Exactly. It queries its local RocksDB to get the exact physical sector offset on the hard drive and grabs the data via raw direct memory access. But before it sends that data back to you over the network, it performs a critical health check.
Dealing with silent bit rot.
Right. Physical hard drives are just magnetic platters. Over time, that magnetic media can degrade. A physical 0 can randomly flip to a 1. That's silent bit rot.
Which is terrifying.
It really is. To catch this, as BlueStore pulls the data into memory, It calculates a dynamic Castagnoli checksum, or CRC32. It runs a complex mathematical check against the raw bytes and compares the result against the golden record it saved when the file was first written.
What happens if the math doesn't match? Do I just get a corrupted file?
You never even see it. If the checksums don't match, the OSD transparently halts the network transmission to your client. It knows its own hard drive has suffered bit rot.
So what does it do?
The server autonomously opens a connection to one of its replica peers, pulls a healthy, clean copy of the data, verifies it, and serves that clean data back to you. The file opens normally.
Oh, I.
And then completely in the background, the OSD uses that clean copy to overwrite its own corrupted magnetic sector, self-healing the cluster.
It fixes its own physical hardware degradation without anyone pulling an alarm. That's amazing.
It's fully autonomous.
And there's one more trick in this read pathway that blew my mind in the source material, but I need you to explain how it works. They call it speculative latency masking.
This is a brilliant optimization for what we call tail latencies. Imagine your client asks the primary OSD for your video file, but that primary OSD is experiencing a temporary physical stall, say a 600 millisecond delay, because the hard drive spindle is struggling to get up to speed.
In a traditional centralized system, you just wait, right?
Exactly. Your application hangs, the loading wheel spins. But in Ceph, there is a speculative timeout physically built into the client software. If the primary OSD stalls for even 50 milliseconds, the client doesn't wait around to find out why.
Just 50 milliseconds.
Yes, just a fraction of a second. The client instantly spawns a parallel duplicate read request directly to a secondary replica node on the network.
So it asks two servers at once.
Right. Whichever node returns the data first is the one the client uses. That 600 millisecond hardware delay is completely masked from the user. You get your data instantly from the backup replica while the primary drive is still struggling to spin up.
Unbelievable. So let's summarize this massive architectural journey.
Let's do it.
By turning physical storage into a deterministic math problem using the CRU-ESH algorithm, they eliminated the central metadata librarian that causes network traffic jams.
Right.
By engineering the BlueStore engine, they completely bypass the heavy toll booth file systems of the Linux operating system to write raw data blazing fast.
Yep.
And by turning individual dumb servers into a self-policing gossip mesh, the system can self-heal, fence out zombies, and fix corrupted bit rot all on its own. It literally breaks through their metadata wall to enable infinite scalability.
And, this raises an important question regarding system design as a whole, far beyond just hard drives.
How so?
The brilliance of Ceph is really an architectural philosophy. It shifts the intelligence away from the center, away from the master controllers and the choke points, and pushes all of that intelligence out to the edges of the network. It empowers the stateless clients and the individual peers to make their own calculated decisions.
And that is exactly what I want you to think about as we wrap up today. We've just seen how eliminating the master controller allowed a digital system to scale to exabytes without breaking a sweat.
It's a huge paradigm shift.
It is. It makes you wonder, look around at the bottlenecks in your own industry, your supply chains, or even your corporate hierarchies. Where else are we relying on a single librarian to do all the thinking, and what would happen if we just gave everyone the algorithm instead?
That's a great thought to leave on.
Thanks for joining us on this deep dive into the source material. We'll see you next time.